Hello all, welcome to the Linux Rootkits for Red Blue Team's course on Pentester Academy. Now in this video, we'll continue to look at other interesting aspects of process information. Specifically, we want to look at the list of open files and sockets. Now the way we can go ahead and get this is inside the task struct. We actually have a member which is a pointer to files underscore struct, and this actually contains information about all the open files. Now it's important to note that in Linux everything is ideally represented by a file. So even sockets both for IPC as well as network ones are really just files. So the files underscore struct will also give us information about open sockets. So how do we go about getting all that info? Now the kernel developers have actually provided a very simple convenience function called iterate underscore fd, where what we have to do is we have to pass this as an input. So we go ahead and pass the files underscore struct as an input. And after that, this function will go ahead and iterate over every single open file. And for every file, it ends up calling a callback function, which is basically to be defined in this format. So basically, it's a function which returns an integer and takes in a void star as the first argument, const void star. And after that, it basically takes in a struct file pointer as an argument. And really what this is a pointer to the file struct of one of the open files, right? And we get this basically for every open file because the function gets called for every open file. And after that you have fd underscore value, which is the file descriptor value. Now once we actually get our struct file, if you recall from the previous video, it's very easy to call d underscore path and actually get back the path to the file. Right? So this is what we do over here. We go ahead, print that. Now there is a possibility that this could actually be a socket. And to do that, we actually have a function called sock from file, where we pass in this file as input. And if it is a socket, then we get back a non-null value. And if that is the case, we are going to print the sock type as well as the address family. Right? More on this when we look at the code. So let's actually jump right in. Now let me go ahead and look at the process library.h file. This is really where we mentioned this. Okay. So here it is. This is the implementation. Let's also quickly look at the task underscore struct. Inside this, you'll actually find that there is a pointer to a files underscore struct, which basically contains all open file information. So if you want to look at files underscore struct, here it is. Right? And if you notice, it says open file table structure. And what we ideally want to do is that we need an iterator which can actually go through this open file table structure. So that iterator, if we do use cscope, is iterate underscore fd for file descriptor. And here it is. So if you notice, it basically takes the files underscore struct as pointer to that as an input. And then it also requires this function it can call back. And this function definition is really what we have mentioned in our library function right here. Here it is, right? So we aren't interested in getting back an argument or doing anything with it. All our interest is in this struct file. Of course, the fd value is also interesting to print, not of any significance for our work right now. After that, as I mentioned, we just go ahead, print that like we did in previous videos using d_path. And then to figure out if this is a socket or not, we call a function sock from file. So search for that, sock from file. And we notice that it actually returns a struct socket, a pointer to a struct socket, if this basically open file is actually a socket, or else it will end up returning null. So that's why we have the check here for null, ensuring that this is not null, in which case we actually know that this open file is really a socket. Now, if you look at the socket structure, here it is. We have a bunch of things in here. Actually, there are a lot of stuff all of these expand to. But the key thing, definitely, what interests us is actually going to be the type, which is right here, type of socket. And what values can actually this type have? So to look at that, let's actually look at print sock type, the function which we have defined. Here it is. And basically a socket can be, a datagram socket, which is UDP, a stream socket, TCP, raw, RDM, sequence underscore packet, etc. I mentioned basically these constants which are available in another file. Actually, it's probably available in this file, net.h. There we go. Right. So we notice it's all mentioned here: stream, datagram, raw socket, reliable delivery socket, blah, blah, blah. So this is how we go ahead and print out the socket type. This is interesting to us. Now, after that, what we also want to know is the address family. So to do that, we have a function called print address family, which we've defined, which is also defined right here. So when this actually receives the socket structure, it goes ahead and looks at ops family. So if we go back and look at the socket structure, what we actually find is there is a ops structure pointer. And inside that, of course, you have a bunch of things, including different operation pointers, etc. But the one we are looking at is the family. And there can be different values, actually many values. So just to show you where that is, here it is. So here are all the different address families. As you can see, there are many of them. What I've done is I've just picked up a couple of interesting ones. So AF underscore Unix domain sockets, used for IPC and a lot of internal stuff within the kernel. Then you of course have inet and inet6. As you can imagine, this is basically your IPv4 and IPv6 stuff. Here is inet and here is your inet6, right? And apart from that, I've also defined AF underscore packet. And for all other cases, I just go ahead and print out the actual numeric value, right? I really don't want to go ahead and mention each and every one of these because we aren't very interested in looking at all. I'm always interested to see AF underscore inet and AF underscore inet6 because it shows that this socket is actually a network stack socket, IPv4 or IPv6. So that is why this is interesting to me. Great. On the main file, we just go ahead and call this at an appropriate place. Here it is. Just call this at an appropriate place and basically say print list of open files and pass the target process's main threads task underscore struct, right? And you can see by creating such a high level abstracted API, once you understand what is happening, you can very easily use this to inspect processes and do interesting things. Great. So now let's go ahead, compile this. Just just make sure this or anything else is loaded. Very good, nothing is loaded. So if I were to do a PS and let's say we want to look at what is happening for our bash prompt, I can do a sudo insmod pinfo.ko process underscore id equals paste this. My bad, before that let me actually clear d message, just makes it easier. If we look at d message, we basically can see that we've printed out all the file descriptors, right? And you can see these are the descriptor numbers followed by the file path, right? Which means there is basically no socket here. Everything is just relating to a file, which is really what is the case for this process, which is okay. Now let's actually look at other processes. Why don't we look at the SSH daemon? I'm sure there will be some network sockets in there. Okay, so bunch of them, we have the daemon process here, and after that probably the process has gone ahead and spawned many of these. Again, you can look at all of this by looking at parent-child relationships. Leave that to you. So let me go ahead, run the program once again, and this time around give the process ID of the SSH process and see what happens. Cool. So now if you notice, we can clearly see that, you know, there are a bunch of file descriptors. But after that, what we actually also find is, for example, this one seems to be a socket, and this is of type sock underscore stream, but this is address family, AF Unix or local. You see another AF Unix local, but then we end up seeing two sockets here which are open. One of them is inet, the other is inet 6, and both of these are sock underscore stream, right? So we will have to inspect more, but huge suspicion definitely is that these are your IPv4, IPv6 sockets, which the SSH daemon is actually binding, right? Now, similarly, why don't we look at, let's say, one of these, or rather one of these, which may also have sockets in them. So I'm going to do a sudo rmmod, then put this one here, type in d message. And we notice in this case, we can definitely see one AF underscore inet socket. Great. Others are local, but this one is actually IPv4, as you can see, right? And again, suspicion is that this is probably the socket being used to connect over the network using IPv4 addressing. Fantastic. So you can clearly see how we can slowly peel away all those layers and start looking at really low level stuff at the kernel layer, right? So hope you enjoyed this video. Try out the code. Please do recommend Pentester Academy to your friends and colleagues. Thank you and see you in the next video.